this video, I'm going to go through the homework for 2.8 to help you get ready for the 2.8 quiz. So the whole focus is on inverses. So remember, for a function to have an inverse that is a function, that function has to pass the horizontal line test. That will mean it's 1-to-1, and 1-to-1 means that it is a function itself and its inverse is also a function. So number 7 is not 1-to-1, because if I were to draw a horizontal line across here, not so much there, let's see, if I was to draw, hold on, escape out of this. Okay, if I was to draw a horizontal line right here, it's going to hit in more than one place. So that's why it's not 1-to-1. Okay, so continuing on to number 9. Looking at number 9, I can draw horizontal lines everywhere. They will only intersect this function in one place. That makes that function 1-to-1, which means it has an inverse that is a function. Okay, for number 11, I drew an orange line right here. That orange line hit my function in two places, and therefore this function is not 1-to-1. So it does not have an inverse that is a function. Okay, so sometimes they give you functions as an equation and not as a graph. When that is the case, you've got to figure out what it is. Okay, this is a line. The line starts at 4, and then you go up 2, over to the left, 1, connect the 2 points, and that's your line. Every single line will be 1-to-1 because it passes the function test, which is the vertical line test, and it also passes the horizontal line test, which tests to see if its inverse is also a function. So lines are always 1-to-1. Here's a radical function. The parent function looks like this. That's going to be 1-to-1. Okay, its inverse is a function because it passes the horizontal line test. This is a parabola. Parabolas are never 1-to-1. Remember, you're going to hit it more than once when you do the horizontal line test. Okay, this is a parabola-like shape. It's a quartic, but it's going to look just like a parabola, only it'll be flatter at the vertex. It will not be 1-to-1. This raised to the 6th power is kind of in the same family here. This will also not be 1-to-1 unless we limit the domain. Limiting the domain is going to make this function 1-to-1. So that's why it's 1-to-1. This function lives between negative infinity and positive infinity. It's going to look like a quadratic, but it'll be flatter at the vertex. If you eliminate everything below 0, you eliminate the failure of the horizontal line test. So therefore, it's going to be 1-to-1 given this domain restriction. Here is a rational function. It will look like this. Given it looks like this, if I were to draw a horizontal line, okay, we're going to do that again. Drawing a horizontal line, I would definitely not pass it. Okay, that line is not going to pass. It's not going to meet the requirement of the horizontal line test because it hits the function in two places. Therefore, it is not 1-to-1. Okay, continuing on. Let's go down to let me see if I can just go down. So hang on. Yeah, so we're on this page still. Okay, we did this in class extensively. When given a function notation like this, the f in function is followed by the x. That's going to always equal the y. Okay, inverses, you flip your x and your y. Therefore, after the inverse notation, which is this f to the negative 1, what's going to follow is the y from the regular first function. Okay, so they're asking you if you evaluate this function at 7, the answer will be 2. Okay, think about that. This is an x. This is the y of the original function. This is the y of the original function. This is the x of the original function. That's why this 2 can go right here. Same thing here. When you're comparing inverses and the original function notation is followed by the x. That's going to always equal a y. Okay, look back at this inverse notation. The inverse notation is always followed by the y from the original function. It's the inverse, you flip x and y. It will always equal the x of the original function. Here's the x of the original function. What's that going to equal? Or in other words, what is the y? And it is 3 because it came from here. Okay, so if you're confused about that, they also address it in the textbook. So I would definitely look at that. Okay, here's a situation where you have your function, it's a line, so you know that this is the x and that this expression is the y. Here, the inverse function notation is always followed by the y of the original function. Since this has to equal the y of the original function, I can set 5 minus 2x equal to 3 and solve for x. That is the x that makes my y equal to 3. To check your work, take this x, plug it in here in your function notation. That means you plug it in here. 5 minus 2 is 3. That's your y value. It all matches up. All right, so you should be able to do that and reason that. Inverses flip the x and the y's. Just keep that in your mind. Okay, continuing on. 29 is very similar to that. Okay, so look what we have. I did this as a warm-up in class yesterday. Here's your f function. That's your regular function. Here are your x's down here. Here are your y's. Feel free to fill this in so you can quickly read it. What they're asking me here is, it says a graph of a function is given. Use the graph to find the indicated values. So what does this equal? This is the y of the original function. That's going to equal the x of the original function. If this is the y of the original function, come down to the graph, go across and read down, and that x is 6. That's how I'm getting 6. Here is function notation. This 5 is the y of the original function. Come to this graph. Here's where the 5 lives. Go across and come down, and you should get an answer of 2 for your x. And that's your x from the original function, which is graphed here. Last one, they're asking you to find the value of x. Given the inverse notation, you know that the y is following. This is the y from the original function. Come over here, 5, 6. 6 is here. Go down and read the x. You get a value of 0. The answers I have down here represent the x's of the original function. The values I have behind the parens of the function notation represent the y of the original function. Keep all that straight and you will be highly successful. Here's another way of thinking about it. It's all the same stuff, presented in different ways so that your brain can kind of wrap itself around this concept. Okay, here's the inverse notation. That means what's following it has to be the y of the original function. They are looking for the x of the original function. Look down here. This is the y of the original function. Go across until you find the 5. Find its partner. It is 4. That's your answer. Okay, moving on. We're now moving into using the inverse function property. That is another way of saying, by using composition, prove that y, or prove that the two functions are inverses of each other. Okay, so composition is when you replace the x in the first function with the entire y of the second function. Okay, so what I do, if I'm trying to find f of g of x, first write down f of x. it would have been 3 times x plus 4. Wherever I had an x, I replaced that x with this entire function. When I did that, the 3's cancel. I now have x minus 4 plus 4. That's just x, and I'm done. I've done a composition. The composition equaled x, so I'm halfway done in proving that these two functions are inverses of one another. Then go to the second function. I'm going to do g of f of x. I would have written down the entire g function, which was x minus 4 over 3. Wherever I have an x, which would have been right here, I'm going to replace it with 3x plus 4. Continue. The 4's will cancel. 3x divided by 3 is just x. And I have proven that they're both compositions, or they're both inverses of each other, since their compositions are equal and equal to x. Okay, if you have difficulty doing compositions, look in the textbook. There's an example there. Come see me, talk to classmates, look back at your notes. We did this in class. Okay, for 43, they ask us to do it by composition again. We're going to prove that these guys are inverses. The goal is to get the compositions each equal to x. Here is my original function. Picture this as being x squared minus 9. I replaced the x squared with my g of x function, which is x plus 9. When I square x plus 9 under the radical goes away. I get x plus 9 and then minus 9, which was present earlier. The 9's cancel because they're opposite signs. I'm left with an x. Do the same thing for g of f of x. Take your g function, which is under a radical. It was x plus 9. What I did, wherever I had an x in that g function, I replaced it with my f of x. Here's my f of x. Inside the radical, I'm going to subtract and add 9's of opposite signs. They're going to fall away to 0. I'm left with a square root of x squared, which is equivalent to just x. I have now proven that these two functions are inverses because both of their compositions equaled x. Okay, continue on down. We're still doing the same thing. We're using the inverse function property, which is code for composition. Okay, so I start out with this f function. Wherever I had an x, I replaced it with this entire g of x. When I do that, in the denominator, these 1's cancel. I'm then left with 1 divided by 1 over x, which is equivalent to 1 times x. That gives me x. Okay, we did some of these in class. If you still are confused about this, look in the textbook, look back in your notes, talk to friends, come see me. Okay, g of f, I start out with this function right here. Wherever I had an x, I'm going to replace that x with this fraction. Okay, so this can be confusing. This double-decker fraction is equivalent to x minus 1. Add 1 to that, the x's cancel, you're left with an x, and you're done. Okay, you now have proven that these guys are inverses because both of their compositions equaled x. Okay, I'm not going to do 47 because I said you can skip that. It's algebraically more complicated, but you're going to get the same result, that those two functions were indeed inverses of each other. Now, this is if I asked you to algebraically find the inverse of the f of x function. So you have steps that you're going to follow. Remember all the time that your goal is to switch your x and your y. So step 1 is right here. Take it out of function notation. Step 2, switch your x's and y's. Step 3, begin the process of solving for the y. So what I did was I brought the 5 over and subtracted it, and then I divided by the 3. Then put it back into function notation using the -1 to represent the inverse. Okay, don't forget this last step. It's integral to the process. 51, same idea. Take it out of function notation. Switch your x and your y. So what I did was I brought the negative 4y cubed over here to the left. I then subtracted the x from the 5. I divided both sides by 4. I am now left with y cubed equals 5 minus x over 4. I do not want y cubed, I want y. Take the cube root of both sides. Change it back to function notation using the inverse notation, and you're done. Okay, let's keep going. Okay, you have a few more algebraic problems to do here. So same steps. 53, add a function notation. Take your x and y and switch it. Then what I did was I flipped both of them over. Or you can do cross products and solve. In any regard, you get this. I'm going to subtract 2 away so I can isolate my y. Here I have it. Change it back to inverse function notation, and you're done. Here, add a function notation, switch your x and your y, do your subtraction so you can get the y on one side and the x on the other side. Because this is squared and I want y, I'm going to take the square root of both sides, and now I'm going to change it back into function notation. Okay, the last one of these deals with a radical. So take it out of function notation, do the switch. In order to get into that y and to isolate it, I have to square both sides. Doing so eliminates the radical and gives me an x squared. Then do your algebraic manipulations, subtract 5, divide by 8. That gives you your y. So here you go. You have your function notation back using inverse function notation, and you have your x squared minus 5 over 8. Okay, then we did 4 graphing problems. Okay, so the key is these black lines that I have on my graphs are all the line y equals x, every single one of them. You don't necessarily need that. However, an inverse is a reflection over that line. So I mashed up my colors. Here's my pink original function. What I did was I found 2 points on that original line, and you should be able to do that. It's clearly easy to find the y-intercept. The way you graphed it is you go to the y-intercept, and then because the slope is 3, I would go up 1, 2, 3 over 1, and I found that point. Take these points and reverse the x and the y. Your x is 0, negative 6 here. So plot the number or the coordinate pair negative 6, 0. That's 1 point on your inverse. Here's the point 1, negative 3. Flip the x and the y and plot the point negative 3, 1. That's your second point. You know it's going to be a line. 2 points make a line. Connect it, and you're done. Okay, 72 is a little bit tricky. That's a downward-facing parabola. So what I did with that is I factored it. And I factored it to 4 minus x, 4 plus x. Then I took note of this domain restriction. So these are the roots. The only root I can use is this one, which is 4 equals x. There's that root. Then I said the y-intercept, which happens where x is 0, 16 minus 0 is 16, I plotted the point 0, 16. Take these 2 points and flip the x and the y. Where I had 4, 0, I now have 0, 4. Where I had 0, 16, I now have 16, 0. Those are your inverse. And you can see, here's your line y equals x. If you envision picking up the orange, which was your original function, and flipping it over or reflecting it through y equals x, the blue follows. So having that there affirms that my answer is correct. Okay, let's go on to 73. So this, let me just go back up so you can see the equation. Here's my equation, radical x plus 1. That is a parent function of radical x, and it's been shifted to the left 1. So I can easily do that. That gives me this point, -1, 0. I then plug in a 0, and I get radical 1, which is 1. That's a second point. I can also get a third point. So I plugged in 3, and I got a y value back of 2. So now I have these 3 points. It traces out my green function. So I know that I am good to go with understanding the original function. I have 3 points. Flip the x and the y. -1, 0 becomes 0, -1. 0, 1 becomes 1, 0. And 3, 2 becomes 2, 3. Connect the points with a smooth curve, and you have your inverse. And again, it looks like a reflection across this line, y equals x, which is what I want. Okay, the last one is another parent function that's been transformed. Look up here, x cubed minus 1. What you can do is you can just plug in some numbers. I'm taking the cubic function and I'm shifting it down 1, and that's what's happening with this graph. So plug in some points, 2 and -8, 2 and +8 will give me some values, I believe, and then plot, reverse those, and you are good to go. Okay, hopefully I did that correctly. I'm just looking at this. Maybe I didn't shift it down. So anyway, the first 3 are good. 74 may have an issue, but concentrate on these first 3. Understand these so that you understand the process of graphically finding your inverses. Okay, so go back over this homework, make sure that you can get the same answers. Look at the notes we took in class, look at your textbook, talk to your classmates, digest the material, come see me if you need to, and you will be highly successful.